Moving on to section 2.3, let's talk about analog I/O modules. An analog inputs and output devices have an infinite number of values, because we're not talking about discretizing what it would be. A typical analog input and outputs vary from 0 to 20 milliamps, 4 to 20 milliamps, or 0 to 10 volts. And so these are some things that you could have, that you're trying to have your inputs and outputs to be within those levels. The analog input interface module accepts an analog signal and converts it to a digital signal. The analog output module accepts a digital signal and converts it to an analog signal that operates the output. Let's think about the types of analog input and outputs. The two basic types of analog input modules are voltage sensing and current sensing. A varying DC voltage in the low millivolt range, proportional to the temperature being monitored, is produced by the thermocouples. And so this is what we're seeing here in this graphic, what it's trying to convey there. What about an analog to digital converter, sometimes called an ADC? The main element of the analog input module is an analog to digital converter. The bipolar input modules can accept signals that swing between a negative and positive value. Unipolar input modules can accept an input signal that vary in the position direction only. And then resolution refers to the smallest change in input signal value that can be sensed. For transducers, the transducer converts the temperature probe variable, that is a temperature, into a very low level electrical signal that is first amplified by the transmitter before being sent on to the analog input module, as we're showing in this graphic. For sensor wiring, wiring 2, 3, or 4 wire sensors to an analog input are possible. And so this gives you an example of what that might look like for each one of those scenarios. For wiring single-ended analog devices, this is what it would look like. You have a power, and then you get into the input and outputs for your controller that we're showing on that other side. Then for the sensitivity of current signaling, unlike voltage input signals, current signals are not as sensitive to noise and typically are not distance limited. The current sensing loop power may be supplied by the sensor or the analog input module. Shielded twisted pair cable is normally recommended for connecting any type analog input signal. So it helps to preserve that sensitive analog signal as you go from one thing that you're trying to connect to another. For a digital to analog converter, also called a DAC, the main element of the analog output module is a digital to analog converter. The analog output module receives from the processor digital data, which are converted into a proportional voltage or current control and analog field device. The analog output signal is varied under the control of the PLC program and can be used for control of an analog control value. The analog I/O control system is what we're trying to show here. The PLC controls the amount of fluid placed in a holding tank by adjusting the percentage of the valve opening. So thus we can have a variable way that we open or close a valve by so many percentage points. The value is initially opened 100%. As the fluid level in the tank approaches the preset point, the processor modifies the output, which adjusts the valve to maintain a set point. We can have scaling. Scaling refers to the changing quantity from one notation to another, and it involves engineering units, the units a human uses and understands, temperature, length, something like that. You can have transducer units, which are either a voltage or current. And finally, you can have binary, raw, or machine units, and the units which a processor requires. And so what we're showing down here is basically binary expression of something. And so for the controller, that would be the kind of way that it would be liking to see information. You can also have SCP, scale with parameter instructions. And so this is what we're seeing here. And you can look at the textbook for more information about that. Okay, let's get into section 2.4, special IO modules. So for high-speed counter modules, high-speed counter modules are used to count pulses from sensors, encoders, and switches that operate at very high speeds. You have the electronics needed to count independently of the processor. A typical count rate available is 0 to 100 kilohertz, which means the module could be able to count 100,000 pulses per second. For a TTL module and encoder encoder counter, an encoder counter module allows the user to read the signal from an encoder on a real-time basis and store this information so it can be read later by the processor. TTL usually stands for transistor logic, in case you're not familiar with that. Stepper motor module. The stepper motor module provides pulse trains to a stepper motor translator, which enables control of a stepper motor. The commands for the module are determined by the control program in the PLC. For motion and position modules, motion and position control modules are used in applications involving accurate high-speed machining and packaging operations. Intelligent position and motion control modules permit PLCs to control stepper and servo motors. For serial communication modules, they are used to establish point-to-point connections with other intelligent devices for the exchange of data. Communication modules provide the connection to PLC networks. Okay, let's talk about specifications. Discrete I/O module specifications. So these are some several pages that we're going to talk about here. So we have the nominal input voltage, the input threshold voltage, the nominal current per input. I'm not going to read these, but if you want, you can pause the video and read these definitions of what they stand for. So these are the first three. Then we have three more: the ambient temperature rating, the input on and off delay, that is a response time, and then we have the output voltage. So these are the things that when you have a module that would be specified. Moving on, we have the output current, the inrush current, and the short circuit protection. These are the definitions for those. Moving on again, we can have leakage current, electrical isolation, and points per module. Then we have this one is on the backplane current draw. And so you only have so much current available. So that even though you may be putting in more and more modules, if you have one that has a huge current draw that maximizes what the power supply can handle, that's going to be it. You're not going to be able to handle anything more. So these were all the discrete. Now we have analog in a similar fashion. We have channels per module, input current / voltage ranges, and the output current / voltage ranges. You might remember when we talked about discrete versus analog, or maybe you can think digital versus analog or something like that. These are the kind of things that we started to talk about. We have the input protection, the resolution, and the input impedance and capacitance. And so these are some electronic type of values when you're talking about circuits that need to be thought about, impedance and capacitance. We have common mode rejection. So that's important. Noise is generally caused by electromagnetic interference, RF interference, and ground loops. And so this is something that for analog signals is especially something that you need to be concerned with. Then, and finally, we have the central processing unit, the CPU. The CPU is built into a fixed PLC, while modular types typically use a plug-in processor module. So keep that in mind. So you have a CPU, a controller, and processor, all terms used by different manufacturers to denote the same module that performs basically the same function. it's kind of gets into how much of a capability do you need in that processor. A processor module can be divided into two sections, a CPU section and the memory section. The CPU executes a program. The memory stores a program along with the other retrievable data. The PLC power supply. The power supply provides the necessary power to the processor and I/O modules plugged into the backplane of the rack. The power supply converts the AC input voltage into the usable DC voltage required by the CPU, memory, and I/O electronic circuitry. For a PLC microprocessor, the PLC contains the similar type of microprocessor found in a personal computer, so keep that in mind. A PLC microprocessor is designed to facilitate industrial control rather than providing general purpose computing. We also have fault-tolerant PLC systems, and this is where you can have multiple more complicated processors to help you out, to make sure that things continue to operate in an industrial environment. You can have various status indicators that are used to provide system diagnostic information so you can quickly get things running. Many electronic components found in processors and other types of PLCs are sensitive to electromagnetic voltages. And so this is something that you need to be careful with how you're handling your electronics. Then talking about memory, memory is the element that stores information, programs, and data in a PLC. And so this is just some information of how that is done. We mentioned 1024, which is 2 to the 10th. And so that's a way of thinking about memory. The complexity of the program determines the amount of memory required. The memory location refers to the address, the CPU memory, where a binary word can be stored. Each binary piece of data is a bit, and 8 bits make up 1 byte. The program is stored in the memory as ones and zeros, which are typically assembled in the format of 16 or 32-bit words. The input status, the sections of memory used to store the status inputs are called input status files or tables. The output status is a section of memory used to store the status of outputs are called output status files or tables. So these are things that you're seeing what it would look like, and then the hardware to give you a perspective on that. There are various types of memory, volatile and non-volatile. Volatile means that when power goes away, you're not going to be able to keep the state, and non-volatile means that you actually maintain the state. So PLCs have programmable memory that allows it to develop and modify control programs. This memory is made of non-volatile, so if the power is lost, it still can maintain its program. You can have read-only memory. This is something that's stores programs and the data that cannot be changed after the memory chip has been manufactured. So this is like cast in stone type of memory. You have random access memory. RAM is designed so that the information can be read into or read from the memory. And so it's constantly volatile and actively used in what you're trying to do with your capability. You can have a erasable, programmable read-only memory. So this is something, instead of read-only memory, you have the ability to actually modify it, but it takes a lot more work. So this is just more information on this type of capability. This is a more specific electrically erasable. Instead of having to have a UV light, you can have an easier way to flash the memory and put in some new things. Maybe if you've ever updated your BIOS on your computer, this would be something that might sound a little bit familiar. For programming terminal devices, a programming terminal device is needed to enter, modify, and troubleshoot the PLC program. This handheld type of unit, proprietary programming terminal, has a connection cable so that it can be plugged directly into the PLC. Handheld programmers are compact and expensive, but a limited display capability. You can also have programming software. The most popular method of PLC programming is a personal computer in conjunction with a manufacturer's programming software. Keep that in mind. Then we have the recording and retrieving data. You can have printers. This would be something that would be familiar. Printers are used to provide hard copies. A printout can show programs of any length and analyze the complete program. So that's something that you can do. You can have memory cartridges. So that would be another way that you can be storing things. And so the cartridge can be used to copy a program from one PLC to another PLC. And we can have a human-machine interfaces. A human-machine interface can be connected to communicate with the PLC and to replace push buttons, selector switches, pilot lights, thumb wheels, and other operating control panel devices. So you can be thinking about that. They provide a means of controlling, monitoring, managing, or visualizing the device processes. The tag database variables are programmed to interact with the program graphic screen objects and communicate with a PLC through the I/O server. You can have screens, and so we had a picture of this at the beginning. HMI operator panels typically contain screens that can communicate directly with the PLCs to read or write memory locations. HMI environmental certification refers to the type of electrical enclosures used to protect the contents from troubleshooting operation conditions. Okay, just to finish up here with a few more slides, HMI alarms are messages which indicate that a fault condition is present. You can have something like inactive, active, acknowledged, or okay. These are some things that you can be dealing with as you're trying to work through some kind of diagnostics. You can also have events and trends. An event history presents a timestamp list of significant events that have occurred. A trend display provides the ability to chart the progress of the process in real time. Finally, you can have a graphics library that provides button, lights, switches, sliders, meters, fills, and other graphic objects that can help you as you try to formulate your displays that you're going to use. All right, well, thank you very much.